So today we're happy to have Vukašin, who will tell us about certain C0 aspects of contactomorphisms.
Thank you, Pazit, and I thank the organizers for inviting me here to give a talk via Zoom. And yeah, so everything I'm going to say is a joint work with Baptiste Serraille. And okay, so let's just get right into it. Okay, very good. So I want to start by reminding something that probably is familiar to everyone, which is the standard non-squeezing theorem. So this is an old result of Gromov, which says that if we take this ball of capacity R and we take the cylinder, which we now also know is of capacity R, but they are defined as in the slide, then simply we cannot map by a symplectic embedding this ball into this cylinder. Okay, as long as you cannot actually include it. So the only way you can map it is by inclusion, more or less, and this is somehow some phenomenon which shows rigidity, and it was a very surprising result, but somehow also one of the starting points of the whole theory. Okay, and now we want to see what happens in the contact case. So in the case of contact manifolds, we want to ask ourselves, is there something similar? And I look at the contact linear space. So it's odd dimensional and has this contact structure given by the contact form on the slide, this one here. And then immediately we can see that if I take the following map, so it's kind of scaling by lambda, and in z direction is scaling by lambda square, then it preserves the contact structure. And as we just put lambda 10 to 0, we immediately get squeezing. Okay, so somehow the situation is a bit more ambiguous because we can squeeze contact balls. Okay, and the question is, okay, let's see how this is somehow fixed. So this is already a little bit less classical, but still well known. So we fix a contact manifold and we look at contactomorphisms, but in the identity component. So we are only interested in kind of contact isotopies starting from identity. And then we ask whether an isotopy can squeeze one subset into another. And here is a definition given by Eliashberg, Kim, and Polterovich in 2006. So we say that U1 can be squeezed in U2 if there is the whole isotopy such that closure of one is subset of the closure of two. And really, I think, I mean, here somehow the point is to look at the isotopy, because otherwise it's just an embedding. And now we say, okay, let's look at the manifold R2n times S1. So pre-quantization space or R2n. And here is a result. So we assume that we have two different radii, small r and large r. And moreover, they are kind of not, we say there is this additional assumption which says that there is an integer in between the two of them. So you can think kind of they're a little bit more far apart, let's say by at least one. Then you cannot squeeze the big ball into the small ball. When I say ball, I mean ball times S1, of course. And okay, this is somehow very nice. I mean, seems like these non-squeezing phenomena generalize. And just a few remarks. So if R and if both balls are kind of below 1, where here 1 is the length of S1, so then you can always squeeze anything into anything. And in fact, in 2017, Chu removed this condition on K. So if one of the two capacities is greater or equal than 1, then in fact, doesn't matter if there is an integer in between, you can not squeeze. Okay, so this is contact non-squeezing. And one more thing which one might naturally ask at this point, I guess, is how do we even construct these isotopies? So, okay, this theorem about something, but are there many isotopies? And okay, so the answer is there is something similar to Hamiltonian formalism, but only in the contact case. So we fix the Reb vector field. So, I mean, we fix the contact form. And then we may again look at the contact Hamiltonian. So contact Hamiltonian is just a time-dependent function, and then you solve this system of linear equations. It always has a solution. And in fact, you can show that what is generated by this vector field is indeed a contact isotopy. So we don't really need to remember all of this. I just want to say that there is a lot of examples. It's similar to Hamiltonian case. For example, if you plug just age exactly equal to 1, you will get back the Reb flow. And in fact, every isotopy can be generated in this way. So this is, again, similar to the Hamiltonian case. We just plug in this tangent to the isotopy in alpha, and we get our function. And okay, so somehow we identify isotopies with functions, and now first goal is to relate this squeezing and non-squeezing to some properties of the group of contactomorphisms. Okay, so that's kind of the starting point. Everything I told so far is relatively classical, and now we put some spin on this. And okay, I will start explaining that. Just first, are there any questions? Okay, very good. If we have an abstract topological group, I want to define what does it mean that the group has Rokhlin property. And the group has Rokhlin property if there is an element whose conjugacy class is dense. So you take all the conjugates, you take the closure, and you get back the whole group. Okay. And so now you might ask, okay, what has and what does not have Rokhlin property? And here are some examples. So the general linear group does not have Rokhlin property. And in principle, matrix groups very rarely have Rokhlin property, or so because the reason is just the spectrum is a conjugation invariant and continuous. So, for example, characteristic polynomial is something that is conjugation invariant. Its coefficients are continuous. So you have just very simple invariant, which is obstructing Rokhlin property, right? Because if the group was Rokhlin, then this spectrum would have to coincide on all elements by the definition. Okay, so now kind of similar example is if we look at compactly supported volume preserving homeomorphisms of, let's say, Euclidean space. Well, now we put on this group C0 distance. So it is defined as it's written. So we look at maximum over x, d of phi of x psi of x. And this group also does not have Rokhlin property. So the reason for that is simply volume of the support is conjugation invariant. So now, I mean, when you realize this, if you think a little bit, you will also realize that it cannot have a Rokhlin property. Okay, but here is something that does have Rokhlin property. So if we drop the volume condition, then just homeomorphisms of Rn with C0 distance compactly supported, this group has Rokhlin property. So it's some kind of very flexible situation. And actually, we will more or less see the proof of this throughout the talk. And here is a compact example. So if you took also homeomorphisms, but which are connected to identity, and the sphere is 2n dimensional, so even dimensional sphere, and again C0 distance, then in this example, we again have Rokhlin property. Okay. And I guess by now it's clear. So I want to somehow study Rokhlin property of contactomorphisms and relate this to non-squeezing. So that's the first goal. Okay, so if we, okay, I wrote contact manifold equipped with Riemannian metric. Probably we don't need this level of generality, but we introduce contact homeomorphisms, which is just the closure of contact of contactomorphisms obtained by isotopies inside compactly supported homeomorphisms with respect to distance C0. And we're, for most part of the talk, going to just be concerned with these two spaces, R2n plus 1 and R2n times S1. And in this case, we equip both spaces with just the standard flat metric. Okay, I will not be talking about the metric anymore. They're always going to be flat. And here is a theorem. So these contact homeomorphisms of R2n plus S1 with the C0 distance, this group has Rokhlin property. And the group, when we do the same thing, but with R2n times S1, it does not have Rokhlin property. And somehow, the way we interpret this is that this squeezing versus non-squeezing is reflected inside the group. And in fact, I will show you the full proof of this theorem. It's completely elementary. And it relies heavily on squeezing versus non-squeezing. So as you will see from the proof. So just before I go on, are there any questions? Okay, I guess not. So let's sketch the proof. So we start first by showing that there's something in chat. What about diff? Well, diff, just diff, or contact diffeomorphisms? Well, it doesn't really matter because in both cases, the answer is that I don't know. Okay. Sure. So, okay, so let's see how this has Rokhlin property. Okay, so we are searching for a G such that con G is dense. So that's what we need to do in order to prove Rokhlin property. So first of all, we start from a sequence which is somehow dense inside the group. We pick any one we wish. And so the idea behind the proof is somehow to compress and pack all of these maps inside a single G. Okay. And how do we do that? Well, compress we are doing by squeezing. So we pick a contact homeomorphism which squeezes the support of Fi into a tiny ball. actually of exponentially decaying balls. The ball of radius 2 minus I. And then we notice this magic identity. So the support of psi I, phi I, psi minus 1. So the support of the conjugate by psi is just the psi of the support. And then we can pack our diffeomorphism as follows. So I just drew the picture. So in the ball of radius 1/2, we put a compression of F1. And then right next to it, in the ball of radius 1/4, we put compressed F2. And then next to it, we put compressed F3, and we continue all the way to infinity. So this is the picture here is representing just one element G. So this is not a sequence of elements. This is one element G in the limit. And you can see that this C0 converges because the balls are getting smaller and smaller. And somehow in this, and it's also compactly supported because it's supported in the ball of radius 1, yes. So somehow we packed all of them into one map. And now I'm claiming this map has a dense conjugacy class. And to see this, what we do? Well, first we pick one Fi, and we single it out by conjugating. So what I'm claiming is that to go from this picture, by conjugation, you can arrive to something like this. So we choose Fi that we want, and we put it all the way up. Let's say I put here height 100, but you can do this by just conjugating. So you conjugate again with the isotopy, which is inside this strip, this tiny strip, and use this support of the conjugate is map of the support. So we single out F1 somehow, Fi, sorry. And then the second thing is we compress everything what is not singled out, what we didn't remove, into a tiny ball. So again, I conjugate and I get a picture like this. So this far away stays what it is, but everything else goes into a tiny ball. And so what we are claiming is that as we let epsilon tend to 0, we conclude that Fi belongs to the closure of the conjugacy class of G. So technically speaking, we didn't prove Fi, but we proved this phi I, Fi, phi I minus 1 belongs to conjugacy class of G, to the closure of the conjugacy class of G. But since this is conjugation invariant, then Fi also belongs. And this is somehow the end of the proof, because if you remember, we picked Fi to be dense inside the whole group. So if you have something closed which contains a dense set, then it's the whole group. Okay, that's the proof of the Rokhlin property. As you see, the key point was that we could squeeze all the time. So we squeeze and squeeze and squeeze until we put all the information we need in one map. And then we can just unpack it and squeeze all the rest to be relevant. And somehow in this way, we are achieving Rokhlin property. Okay. Now let's see how to show non-Rokhlin property. So the claim is that if I look at the following space, then it does not have Rokhlin property. And the idea is, again, we will use non-squeezing in this case. And this proof is very short, actually. So if you assume there is G such that conjugacy class of G is dense, then it is supported inside some large ball times S1, just by compact support assumption. And now we want to take another element which kind of moves much larger ball. So we take an element which has no fixed points in this ball of r plus 101 times s1. And you might ask, why do we know this exists? But kind of just the red flow on this manifold is rotating in S1 direction. So contact Hamiltonian of the red flow is just identity. And I can take a function which is equal to 1 over this ball and then cut it out somewhere at infinity. And then take a small time isotopy of this, of such cut out red flow. So no problem to construct this. And now the claim is if F was actually in the closure, then if you take sufficiently close conjugate of G, this map also moves everything in a slightly smaller ball. So ball of radius, let's say r plus 100. So now we see that somehow we can conjugate something supported in a small ball to move everything in a large ball, and that's kind of fishy because I can just write the following sequence of inclusions. So this ball of radius r plus 100, it's inside the support of psi g psi minus 1, which is psi of the support of G. But this is a subset of psi of BR times S1 by assumption. Okay, and now you act by psi minus 1 and you actually get squeezing. So the big ball is squeezed into the small ball. And this is a contradiction. I mean, if you have non-squeezing, you also have a non-expanding kind of. So that's the whole argument. Okay, so this sample theorem, I showed the whole proof, and okay, let's see any questions now. No? Okay, so let's move on. Somehow we studied this Rokhlin property, but I mean, it's more like an illustration of something you can do in elementary terms, not kind of the main goal of this whole project. And okay, previous proof relies only on non-squeezing. Yeah, so sorry, I want to comment. Yeah, so it actually extends this proof to completion of a Liouville domain times S1 if the symplectic homology of the domain vanishes. Kind of the same exact proof, you just use a different non-squeezing result proved by Albers and Mary. Okay, so what I started trying to say is how to go beyond the Rokhlin property. There's something in chat. What is SH point? It's a symplectic homology, but generated by contractible loops. Okay, so how to go beyond thanks. Sure. How to go beyond Rokhlin property? Well, we need to recall how in the first examples we were actually showing Rokhlin property. So these were the two examples, and the way we showed it is we said, okay, here we have spectrum, it's preserved. Here we have volume of the support, it's preserved. So something is preserved, but moral of the story is somehow, as long as you have something which is conjugation invariant and it is continuous, well, that thing will somehow obstruct Rokhlin property. So what we would like to have is somehow, yeah, also another thing which we would really like to do is to somehow study geometry of conjugation classes. So that would be pretty cool. So, okay, so now the utopistic situation is to have a C0 continuous and conjugation invariant norm on cont. So that would be kind of a complete utopia and everything would be great. But we have this anti-utopian theorem, which says that if you have a conjugation invariant norm, it can never be continuous with respect to any reasonable topology on the contactomorphism group. So what does this theorem actually really... so what does it mean, reasonable topology? So it means any topology for which identity is not an isolated point. So kind of, I mean, any topology you normally think of. Of course, if you put a complete discrete topology, everything is continuous, but yeah, it's a big pity. But okay, sometimes we can maybe we can get rid of this continuity, and we refer now to a theorem of Sandon. Yeah, I forgot to say this theorem. First theorem was proven by Burago, Ivanov, and Pulterovich. And so theorem of Sandon says there exists a conjugation invariant norm on this group, contactomorphisms of R2n plus 1 times S1, but it is integer valued. And this norm is in fact unbounded. Okay. So you need to know these facts, but what we propose is, okay, we don't really want continuity, but we want to show that gamma is locally bounded in C0 topology. And somehow, if you have continuous something, then of course you are locally bounded, because in every neighborhood, your values take value which is nearby the value of the point. But if you're locally bounded, you can still do a lot of things with this. And yeah, just to remind you, this means that in some C0 neighborhood of identity, gamma is bounded. So we want to stick to this notion, and in fact, our first result says that gamma is in fact C0 locally bounded. So here is the result written precisely. So if you take an isotopy, this isotopy is on distance 1/2 from identity. So then gamma is less or equal than 2. So this is exactly, so in some neighborhood of the identity, gamma is bounded, but we just made the constants explicit. And yeah, another remark is that somehow from this thing, I mean, why put this in the same theorem, that gamma is C0 lower semi-continuous? Because actually the proof that gamma is C0 lower semi-continuous relies on this somehow. Okay, so this is some almost utopia situation, because now you can extend gamma to the closure just by taking lim-inf, as one always extends lower semi-continuous functions. And then now we get this gamma tilde, which is conjugation invariant norm on the contact homeomorphisms. It is also C0 locally bounded, and it is also C0 lower semi-continuous. Okay, and okay, so that's kind of maybe the punchline. So maybe I'll stop a little bit to see if there are questions. No? Okay, maybe later. Very good. So let's see some applications of this. So we obtain this norm, and so what? Well, first of all, we say that this somehow is giving a restriction on conjugacy classes of elements. So the claim is the following: if closures of two conjugacy classes somehow intersect, then gamma tilde of these two elements is close by. And I mean, the proof is two lines. You take an element in the intersection. What we proved so far is that these two gammas of the two elements is somehow squeezed in between gamma of G and gamma of G plus 2, and that's QED. But now notice that this immediately implies Rokhlin property, because assume this thing was Rokhlin, then the whole group is in a closure of something, which means that the whole group is kind of on distance 2 in this norm from the thing. But this is impossible since gamma tilde is unbounded by Sandon. Okay, so this gives us a tool to study somehow a little bit more conjugacy classes without actually. So somehow this squeezing, non-squeezing is very synthetic. So it can tell you a criterion whether something is Rokhlin or not Rokhlin, but it cannot really measure whether two classes intersect or not. You cannot tell such a thing. But this is a little bit like more conceptual proof. And okay, we want to see further where this leads us. So what more can we extract from it? So here is another application. So now we start from arbitrary contact manifold. And okay, we look at, we want to define contact fragmentation norm. So I need to remind you what is a contact fragmentation lemma. So you just take Darboux balls inside your contact manifold, and you want to split your contactomorphism inside of these Darboux balls, somehow as a composition of things supported in the Darboux balls. So we cover the whole manifold by Darboux balls, and here is a result of Banyaga from 78. So if you have a contactomorphism, which is kind of coming from an isotopy, then there are some elements, phi 1 to phi n. Each is supported in one of these UI, in one of the Darboux balls, and your whole phi just decomposes as into these elements. Okay, and now we define the norm with respect to the covering U as minimal n, such that we can do this. And contact fragmentation norm is then minimum over all covers of these norms. This contact fragmentation norm, and this is in fact a conjugation invariant norm on this group, and clearly integer valued, as one can see. And this is very classical. I mean, okay, so Banyaga proved this fragmentation theorem. So the actual norm, I think maybe was first introduced in this paper of Burago, Ivanov, and Polterovich. I could be wrong, but I'm under this impression. So it's a kind of still at least 20 years old, probably older, this concept. And we want to somehow we want to, okay, so this relies in some covering by balls and then this fragmentation theorem. So it's kind of very specific. It relies on, you need something like a manifold, right? And then you need to have this lemma actually. And we want to somehow have some analog in very abstract terms of this. And we propose the following thing. So if you have a topological group, and then you look at elements such that identity is in the closure of the conjugacy class of each element. So these SG you think of as things supported in Darboux balls. And now if this is a generating set, then we can define conjugation norm by looking again at the minimal number of such generators which decomposes the element. And this is always a conjugation invariant norm on the group G. But if we go back to contact manifolds, now if something is supported in a Darboux ball, then identity belongs to the closure of the conjugacy class of that, because you just squeeze it. And it is works for contact fragmentation, it works for any fragmentation. So if you're supported, for any fragmentation by something that can squeeze balls. So if you're supported in a Darboux ball, you can squeeze everything to a point, and then identity is in the C0 closure, and you get the following thing. You get this inequality. This norm is less or equal than fragmentation norm. Okay, so maybe you ask, why am I doing all of this? Looks abstract, but in fact, because of this C0 almost continuity of gamma, it immediately implies the following thing. So 1/2 of gamma is less than this norm on the contactomorphism group, which is less than fragmentation norm. And since gamma is unbounded, you now notice that fragmentation norm is unbounded. And so I want to say that this actually was first proven in 2013 by Kolan and Sandon, and then again reproven by Fraser, Polterovich, and Rosen in 2018. And this is a third proof. And I would say that these proofs are kind of independent. So Kolan and Sandon also construct some metric which is less than fragmentation norm. And Fraser, Polterovich, and Rosen show that kind of under some assumptions, anything is more or less than fragmentation norm up to constant. And we somehow go through this C0 procedure. So maybe philosophically, our result is similar to Fraser, Rosen, and Polterovich, but in somehow C0 setup, let's say. Okay, and now in the rest of the talk, I have 25 more minutes. So I will discuss gamma. So this gamma is somehow an important thing, and I want a little bit maybe explain some context and maybe tell you a little bit how it's defined, and maybe comment very briefly on the proof of all of the local boundedness. Okay, so we start with context because it's like taking a break from all of this. Okay, so context, here it is. So first, we start with the Hamiltonian case, compactly supported Hamiltonians, and in 92, so this theorem is as old as me, it was proven that there exists gamma, which is conjugation invariant norm by Viterbo, it was proven, and it is in fact C0 continuous and unbounded on this group. And somehow the way this was constructed is using generating functions. And then later there have been Floer theoretical approaches, so notably by Schwarz and Do. And the C0 continuity of these invariants coming from Floer theory, it's kind of still an active thing which people research. So I think I listed all the results I'm aware of. So there is a paper by Seyfadini, and then there is paper by Buchowski, Humilier, and Seyfadini. Then there was a paper by Yegor Shelukin and a paper by Yusuke Kawamoto. And in the contact case, Sandon somehow mimicked more or less the construction of Viterbo. Of course, there are some subtleties. It's not obvious how to mimic it, but at the end of the day, it is pretty analogous. And then Floer theoretical methods here are kind of now, I would say that we are in the stage where we are doing Schwarz and O, but in contact case. So all these works are very recent. So Alberts and Mary wrote a paper which was published 2018. And then Dylan Kent and Daniel Georgievich, Igor Uljarevich, and Jun Zhang, these are two preprints, so not published yet. Very recent, and Alberts, Shelukin, Zapolsky is work in progress. So kind of Floer theoretical approaches are very much in development at the moment. And our result is somehow trying to be analogous to this C0 continuity results in the symplectic case. And I should mention that we actually prove C0 continuity of some invariants, both for Sandon and for Albertson-Merry, from which the actual norms are derived. So it's really kind of analogous if you go into the proof. You see that it's also some kind of C0 continuity. Okay, so this is all the context. Now let's see a little bit the definitions and properties of gamma. So first notion I want to introduce is that of a translated point. So if you have an element in this group, okay, so this is also more general notion. I'm just writing it for this group we are interested in. So we say that something is translated point if Q and phi of Q lie on the same S1, on the same circle, and this alpha 0 is the standard contact form. If you pull back it and evaluate at Q, you are getting again alpha 0. Okay, so the real notion would be something which maps Q maps by phi to orbit of the Reb flow. So somehow Q and phi of Q are on the same trajectory of the Reb flow. But since here this is just rotating in S1, they're on the same S1 circle. And we can define the action of such a translated point by simply seeing how much angle it rotates. So if you would project kind of all the time to S1 and just see the rotation in this direction, this is the action of a translated point. In general, the action is somehow the length of the Reb chord which connects the two things, but here it can be written just like that. And then the spectrum of a map is just the action of all translated points of the map. And in fact, in this case of compactly supported maps of R2n times S1, it only depends on the time one map, not on the whole isotopy or anything like that. And it's a uniquely defined subset. And now Sandon constructed spectral invariants, which map actually this group into R. And they are defined using somehow this homological min-max in the standard way, as always. But the point is to use a filtered generating function homology. So somehow there are generating functions for contact isotopies, and you use this, and you need to prove a little bit that they are actually invariants. There is some work, but at the end of the day, it's homological min-max. And they, in fact, belong to the spectrum. That's why they're called spectral. And okay, this inequality, I mean, okay, so maybe I don't want to comment on this, but we will use this. So these two invariants, one is less or equal than 0, and the other one is greater or equal than 0. Very briefly, you think of the smaller one as the point class invariant and of the larger one as the fundamental class invariant. And because you're compactly supported, you kind of have 0 at infinity. So this one must be less or equal than 0, and this one greater or equal than 0. That's the intuition why this happens. Okay. But there is an issue in the whole story. So that this issue is that translated points are actually not a conjugation invariant notion. So when we do flirt theory, we say, okay, we have a fixed point, and then I conjugate, and this is, then if I conjugate by some psi, then psi of Q is again a fixed point of the conjugate. But this is not the case for translated points. So somehow one needs to overcome this. And this is, so this C minus and C plus are also not conjugation invariant. So Sandon did overcome this, and I think this is a nice insight. So we take somehow integer parts. So these are the invariants we actually want to look at, lower and upper integer parts of C minus and C plus. and they are conjugation invariant. And integers, again, are the length of S1. So somehow the period of the Reb flow, that's why integers show up all the time. And so they are conjugation invariant, and in fact, they satisfy what everything nice, which Flirt theoretical spectral invariant satisfy. So there is this inverse property, and then there is this triangle inequality. And okay, now when we arrived already this far, you just, take the difference and you will actually create a bi-invariant metric. And that's what Sandon did. And you see now it's integer valued because of all the integer parts everywhere. Okay, and so how to prove it is actually C0 locally bounded. This norm, well, okay, this notation, we just denote the distance from phi to identity by C0 distance of I. And here is a proposition. If this norm is less than 1/2, then the whole spectrum is just inside of this interval. So I want to make a remark that this actually has nothing to do with any homology. So there are no spectral invariants. This is completely elementary. And in fact, the proof is very much short and elementary. There is a trick inside. It's not trivial, but actually, maybe now that you know, you can do it this way. Maybe it's a homework. I mean, who is interested to try to do this as an exercise? And the solution book for exercises, it's in our paper, but it's really not very difficult. So, but this fact immediately implies that somehow these C- and C+ are squeezed between the norms, and then in fact, if you take integer parts, then you get the local boundedness. Okay, so that's more or less everything I want to say, but I anticipated I might finish a bit earlier because somehow I'm not writing anything, so I go fast with slides. So there are bonus slides, so which I will just show some stuff which are I don't know. I mean, I hope you find them interesting, but okay. So here is the thing. So first bonus slide is talking about somehow really how can we quantify Rokhlin property. So Rokhlin property is just property, but can we make some quantitative version of it? So here is an attempt. So if you take a topological group, you say that two elements are conjugation connected, actually K conjugation connected, if you can build a bridge built out of conjugacy classes between them. So you somehow call the first one phi 0 and the last one phi k. And then in between you put phi 1, phi 2, phi 3, phi 4. So, and then for each consecutive phi I and phi plus 1, there exists some psi whose closure of the conjugacy class passes through the two of them. So you really kind of have two elements which you think kind of they are far away. You put in between these stops, phi 1 to phi k minus 1, and then you connect everything by conjugacy classes. And then you define a distance between two elements of the group as the minimal k, such that these two are k conjugation connected. And now we notice the following thing. If G has Rokhlin property, then this metric is just trivial in a sense that it is 0 if F and G coincide, and it is 1 if F and G are different, because any two elements can just be immediately connected by this Rokhlin element. However, in general, it's not equivalent. I mean, this fact that the trivial metric is Rokhlin property, but the bigger the metric, the more Rokhlin property fails. You can think of it this way. So kind of showing that this metric is big really means Rokhlin property is failing badly. And okay, so we show that this has unbounded diameter. And this is actually very simple again, because by everything I've said is it implies that somehow you have that if you have these bridges, then you apply on every conjugacy class the result for gamma, and you see this. Okay. So that's one thing. And okay, for the last bonus slide, I'm gonna give some open questions. So these are things which we don't know how to do, and you maybe potential next steps, some of them. So first question is, does closure of contactomorphism group of S3 have a Rokhlin property? Okay, first, let me note that in the compact case, we could do so just for homeomorphisms, not contact homeomorphisms, just for homeomorphisms, we could do this for the even dimensional sphere, but not for the odd one. And the reason why it can work for even dimensional sphere is because every homeomorphism of the even dimensional sphere has a fixed point. And then somehow you start from this fixed point, you do something local in a neighborhood, and then the rest of the sphere you treat as if it was a ball. And for the ball, we saw the argument somehow. And but in the odd dimensions, this argument does not work. And as far as I could see in the literature, I was looking a little bit. I mean, I'm not really an expert on this outside of symplectic topology. So as far as I could see in the literature, this is not known for odd dimensional spheres, even for homeomorphisms. But maybe in the contact case, there can be some techniques which show this. I don't know, because these papers I cited of Dylan Kent and Georgievich, Uljarevich, and Zhang, and in progress of Albers, Shelukin, and Zapolsky, they actually deal with the closed contact manifolds, and exactly of this type. So they are kind of pre-quantization bundles. So so this S3 is very good kind of case to try it. But one caveat to note is that fragmentation norm is bounded here. So you cannot really get something as simple as we do, just argue by unboundedness. You need to be very precise. So I'm not sure. This might actually be a very hard question, but looks like not infinitely far away from the methods which we have. Perhaps solvable. Okay. So that's question number one. Any questions about the question? No? Okay, question number two is, can one prove a contact fragmentation for contact homeomorphisms? So there is some work in the Hamiltonian case for Hamiltonian homeomorphisms that was done by, originally, if I'm not mistaken, no, actually probably by Baptiste Serraille, the co-author on this paper, and but motivated by some previous work of Pierre Polterovich and P. And then there is also a recent result of Habib Alizadeh, who is, by the way, a PhD student here in Montreal, but he is not here. He's actually in US. So also in the Hamiltonian case, and I don't know, in the contact case, as far as I know, no results of this type. And I think it would be interesting just in general, but from the perspective of what I talked about, if such a thing would exist, then the fragmentation results which we mentioned could maybe be proven also for in this way for contact homeomorphisms somehow.
So, sorry, Vukašin, do you mean if there's a C0 fragmentation, elements in there?
Well, I mean, just fragmentation, but by elements from the contact homeomorphisms of the contact homeomorphism. I don't know what you mean by C0. I don't ask any bound on it. Just if I take a homeomorphism and then Darboux balls, can I split it into homeomorphisms supported in Darboux balls?
Ah, okay. So just Banyaga type fragmentation or whatever.
Right.
Yeah, okay.
Right.
Okay.
Because Banyaga's proof relies on using the isotopies somehow.
Yeah.
Right. Yes. So then there is this embarrassing question, which is this actually equal to frag? Okay, so we actually tried to prove this, and I'm pretty sure the answer is no, but we could not construct an example, unfortunately, because so imagine the answer is yes. So these two norms are equal. What that would mean is that whenever you have an element who, when you conjugate it, can convert to identity, it has to be supported in a Darboux ball. So this seems very non-intuitive because one can imagine that at some point you are rotating something, but then you somehow close up in the limit. Like you are rotating more and more and more, and you are not really violating anything, but then in the limit somehow you close up. But then maybe if what I'm imagining, this closing up is non-contractible, maybe you can rule it out. So maybe it actually has to be contractible, and maybe there is a ball. So I actually don't know what to think. I would guess that they're not equal, and that we just couldn't construct a simple example, Baptiste and me. But it would be more, more exciting if they actually were equal in some cases. But I think this question is actually approachable. I mean, we couldn't do it, but I don't think it's somehow extremely difficult. It's just maybe need to be a bit more clever. Okay, and so this question is maybe the last one, I think, or maybe there is one more. So this question is, can it happen that actually for two fixed elements, this, which I just last defined, this matrix CC is actually infinite? So I a little bit cheated. I said, okay, let's take these elements, which are bridges, and connect everything, but maybe they don't exist. Maybe you can just not build a bridge between two elements. And actually, this is related to some well-known thing called weak conjugation equivalency. So this, okay, so I don't know the actual origins of this notion. I learned it from a paper of Leroux, Seifadini, and Viterbo. So they have a paper which is studying this notion, and the notion is kind of two elements are weakly conjugation equivalent if any continuous conjugation invariant map from the group to some Hausdorff space coincides on these two elements. So imagine you could build this bridge I'm talking about with conjugates, then somehow on every bridge this map is constant, and then it coincides on the two elements. So in particular, they need to be weakly conjugation equivalent, and actually we don't know if there are elements which are not in the case of R2n times S1. So somehow here the belief, which also we couldn't prove unfortunately, is that maybe there are elements which are not weakly conjugation equivalent, but still this no, sorry, vice versa. What is the belief? 1 second, I need to think. Right. So okay. I think we concluded there might be some elements in which you cannot connect. This is maybe possible, and we had actually no clue whether you can have two non-conjugation equivalent or not. I mean, bottom line is I think we actually don't really know what is the answer to this question. But also this I think is still approachable. So 3 and 4 are somehow approachable, and 1 and 2 I'm not so sure. 2 is probably very hard, and one is maybe hard, maybe not. Probably hard. Okay, and yeah, this is the last one. So this is asking if this DCC is bounded for pre-quantization spaces of Liouville domains. So I actually think that this question is not hard. I mean, but the point is we prove continuity of Albers-Merry spectral invariants, but they did not prove the triangle inequality. So these spectral invariants don't produce a norm. And the issue is purely technical because you need to somehow analyze some product on Rabinowitz-Floer homology. But I think with these recent advances in Floer theory, this question you probably can just solve if you work out the products or just apply it to some different scheme where you have triangle inequality. And then I think this is more interesting is what can you say about not pre-quantization space, but this omega times r. So now omega hat is like r to n, and times r you get back to r to n plus 1. And we knew it is Rokhlin in this case, the group, and perhaps this DCC is bounded. So you can have maybe not Rokhlin property, but you can have a bounded distance instead. Okay, so that's it. Thank you.
Thank you, Vukašin. Any questions?
Yeah, I have a question, Vukašin. Thanks for the talk. Have you thought about the strict contactomorphism group? So even if you take like R2n plus 1 with standard contact form, but then you look at strict contactomorphism, do you have squeezing or not?
No, but you should have volume preservation, right?
Sure.
But then you cannot squeeze, I think, because the volume of the larger ball is larger than the volume.
No, but I mean like in symplectic, like a large ball in a thin cylinder, or things like that.
Ah, oh, so you mean like Gromov type result for strict contactomorphisms of R2n plus 1?
Yeah, exactly.
I have not thought about this question, but it's I would assume someone did. I don't know. Audience. It's like in this quiz called the audience. But it's a good question, by the way. Unless it's trivial, then I will retract. But sounds like a good question.
Can I ask a question? Yeah, so is it, I mean, have you thought about the homogenized Sandon norm? Is there a chance that this could be C0 continuous or?
By homogenized, you mean
you take limit of gamma of phi to the k divided by k.
I have not thought about that.
Okay. And another maybe related question is there are some quasimorphisms in some cases on the group of contactomorphisms. And is there anything known on their C0 continuity or some open questions?
Yeah. Yes, so I think the answer to this is actually no. So this, I mean, I don't know, but I think in this case, I don't know, not because I'm ignorant, but I think it's not, I don't think it's known.
Ah, okay. No, in the sense it's not known. Okay.
I think so.
Okay.
But this is, of course, very interesting and probably natural kind of natural, I would say, maybe next step to try to investigate this kind of stuff or whatever can happen with quasimorphisms. I don't know. I mean, maybe don't really ask for C0 continuity, but for something, I don't know, some C0 property.
Mhm. Mm. Okay.
Very
Thanks. I think in the chat, I think.
Yeah, there's something in chat. If the contact isotopy is strict for all times, then it is the lift of Hamiltonian isotopy. But the question was for R2n plus 1, right? But okay, you say then, yeah, this does not have to be a lift. For example, what? Is this even true? Okay, yeah, it is true, yes. Right. But still, I mean, I don't think it changes much because can you comment on the difference between Rokhlin property for cont and the universal cover of cont? Can I comment on that? Well, for universal cover, yes, I understand why. But for universal cover, it's probably more difficult, right? Because you not only need to somehow approximate the time one map, but you need to approximate, in fact, time one map inside some homotopy class of paths. So I would say if you can prove it for universal cover, probably you already can prove it for the group. So I think the group question is probably easier, right? Unless I'm missing something.
Okay, so if there is no more question, thanks Vukašin again.